Okay, so let's state these limit laws. And this will be without proof. Okay, so you don't have to worry about any proofs for this. Yeah, this ping. Did everyone do the reading on limit laws? You all did the reading. Okay. Remember, I can check if you did the reading. Okay, limit laws. Okay, so suppose that we have the limit as x goes to a f of x, and the limit as x goes to a g of x exist. Okay, we know what that means. For a limit to exist, the left and the right limits must agree. Okay, so number one, the first limit law. If we have the limit as x goes to a of f of x plus or minus g of x, then this is the limit as x goes to a f of x plus minus the limit as x goes to a of g of x. So the limits can distribute over the plus or minus. So if we have the sum of two functions where the limit exists for each of them, then we can do the limits individually and then add the results. Okay, number two, the limit as x goes to a of some constant k times f of x. This constant, it doesn't affect the limit. We can take it out of the limit. So this will be k times the limit as x goes to a of f of x. And again, constants, multiplying the functions, they don't affect the limit value. We can take it out of the limit and then just do the limit of the original function. Okay, number three, we have the limit as x goes to a, f of x times g of x. Okay, so if the limit of f of x exists by itself and the limit of g of x exists by itself, then we can do them separately and then multiply the answers. So this will be the limit as x goes to a f of x and the limit as x goes to a of g of x. Okay, so on the right-hand side, we multiply the result. This we're going to use many, many times. Okay, this number three. Okay, number four, we have the limit as x goes to a of f of x over g of x. Okay, very similar to number three, but now we've got the quotient. Again, if the limit of f exists and the limit of g exists, we can do it separately. So this is going to be the limit as x goes to a f of x over the limit as x goes to a g of x. Okay, but whenever we've got fractions, we must be careful. The denominator can't be zero. So we need to put the restriction that the limit x goes to a g of x is non-zero. Right, we don't want to be dividing by zero. Okay, and number five, we have the limit as x goes to a f of x to some power n, whatever power that might be. This is equal to the limit as x goes to a f of x. So we do the limit first, and then we do the power on the outside. Okay, so if we have, for example, the limit x goes to a of x squared, okay, if the square is just some power, we can take the limit inside and then square the result. Later on, we will extend this not just to powers, but any continuous function. Okay, but we don't know what that means yet. We'll see that much later. So we will extend this property to any continuous function. Yeah, so not just powers, it will be any continuous function. And the vast majority of functions that we're going to be working with are continuous. So this property number 5 becomes very useful later on. Okay, so these are just a few properties to learn for now. They'll help us when we're doing algebra problems with limits. Again, especially this number 3 here. If you have the limit of two functions being multiplied, if we know the limit of the one part and the limit of the other part, we can just do them separately. Okay, so together it might look complicated, but if you can split it up into two parts where the two parts are easier to do, then number 3 allows us to do that. Okay, so complicated problems, we can split into two easier problems. Any questions on these? All good. Okay. Next, the squeeze theorem. Okay. So when evaluating limits, there's a number of tools that we use. So the first one is these sets of 5 limit laws. So that's your first tool. The squeeze theorem, that's your second tool we're going to use. And then later on, we're going to have L'Hopital's rule. That will be your third tool. Okay. So limit laws, that's the first thing you should think of when evaluating limits. Squeeze theorem, that's the second thing. And then in a few weeks, when we do L'Hopital's rule, that will be the third thing. Okay. Once you know all 3, you can evaluate any limit given to you. And this will be without proof. Okay, so we'll just state the theorem, we'll use the theorem, but we won't be proving the theorem. Okay, so imagine we have 3 functions f, g, and h, and they are ordered like this. So at the top, we have a function f. In the middle, we have a function g. And then underneath all of that, we have a function h. So f, g, h, they can be any functions, piecewise functions, parabolas, hyperbolas, whatever types of functions. 3 functions f, g, h, where f is on the top, g is in the middle, h is on the bottom. And we are interested in this point over here at x equals a. Okay, so 3 functions. And then around x equals a, the functions are close together. Okay, we'll write that out precisely. But from the picture, you can see that around x equals a, f, g, and h are fairly close. But over all of those x values, f is above, g is in the middle, and h is at the bottom. Okay, that's a requirement. Okay, so if h of x is less than or equal to g of x, which is less than or equal to f of x. So again, f, that's at the top, g is in the middle, h is at the bottom. And so that's the first requirement. The second requirement is that the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x. So these must agree. Let's call it L. Okay, so the limit of f, that's the upper function. The limit of h, that's the lower function. They agree, being equal to L. Then we can conclude that the limit as x goes to a of g of x is also L. Yeah. So what's the idea behind this? Well, we can see that around x equals a, this function g is squeezed, squeeze theorem, is squeezed between f and h. So here we've got g is squeezed between f and h. So f at the top, h at the bottom, g is squeezed between the two. If the top function and the bottom function have the same limit value, then looking at it at the top, f is going to have some limit value, h is going to have the same limit value, so they approach the same point. Think of it like y values. At x equals a, f is going to have some y value, that's going to agree with the hy value. Okay, so just imagine we have that over here. So here, this y value and this y value here. In the limit, they get very, very close together. They squeeze g, and since f and h have the same limit value, g being squeezed between the two will have the same value as well. Does that make sense? Yes? No? No. Okay, so let's draw a little picture here. Okay, so we've got three functions like that. There's a y value here, a y value there, and a y value there. Let's call it 1, 2, and 3. Okay, if 1 and 3 get closer and closer until they touch, what can we say about 2? It's the same. Okay, if 1 and 3 get closer and closer until they touch, we always have the same order, 1, 2, and 3. 1 and 3 end up touching, 2's in the middle. They're all touching at the same point. They all have the same value. They all have the same limit value. Make sense? Okay. Okay, so that's the squeeze theorem. You might also see it as the sandwich theorem, but in the textbook, it's squeeze theorem. Okay, let's have a look at an example. Okay, so we've got the limits as x goes to 0 of x squared sine 1 over x. Yeah. Now, if we just look at this like the limits we covered before, we've got a problem. Because when x goes to 0, we have there 1 over x. We can look at it from the left, we can look at it from the right. It's not going to help us. 1 over 0 is 1 over 0. We've got a problem. So what we want to do is try and build up this function such that we have the following. We have three functions where the given function is in between the two. Okay, so g of x, that's going to be the one that's given. H and f, we need to find those such that the h limit and the f limit are the same and easy to calculate. So that's the idea. So what do we know about this function here? We know that the sine function is always bounded between -1 and 1. That's what we know. That's a good starting point. So -1 is less than or equal to sine of 1 over x, which is less than or equal to 1. Doesn't matter what we put inside the sine function, the graph is always between -1 and 1. Whatever value you put in, it is always between -1 and 1. Okay, so that's a good start. But what we actually have is x squared sine 1 over x. Over there, we've got sine of 1 over x. Let's multiply through by x squared. So we're going to have minus x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. So now we have our f, g, and h. The function we're interested in is in the middle. The functions on either side are very simple, and we can calculate the limits. So let's do that. So we have the limit, x goes to 0 of minus x squared, less than or equal to the limit as x goes to 0 of x squared sine 1 over x, which is less than or equal to the limit x goes to 0 of x squared. Okay, so we just took the limits throughout. Now, what we're interested in is finding the first limit and the last limit and checking if they agree. If they agree, then that is the same limit value as the middle by the squeeze theorem. So let's check. So we've got the limits as x goes to 0 of minus x squared. What's this going to be? Think of the picture. We're going to 0. What do we get? 0. Okay, if you're stuck, draw a picture if you need to. But if we got the parabola unshifted, the turning point is at 0. So when x goes to 0, the function goes to 0. Okay, what about the other one on that right-hand side? X squared instead of minus x squared. What's the limit? 0 also. So here we have 0. Limit x goes to 0 of x squared is also 0. So f, g, and h, they're all going to have the same limit value by the squeeze theorem. Therefore, the limit as x goes to 0 of x squared sine 1 over x must also be 0. The left one 0, the right one 0, the middle one must be 0. Why? Well, by the squeeze theorem. Okay. Any questions on this? Oh, good. Okay, so the idea of using the squeeze theorem is always the same. We've got some function in the middle that's bounded between two values. For example, sine of 1 over x, or we could have cos of x, anything like that. Then what we do is we start with that and we build up to what's given. So we know that sine of x is bounded, like cos of x is bounded. But over there, we've got x squared sine 1 over x. So we multiply through by the x squared. Now, the middle term is what we wanted. We take the limit of the left and the right ones and check if they're equal. If they're equal, then the middle term has the same limit value. Yeah. If they're not equal, well, try something else. Okay, squeeze theorem doesn't work in that case. Okay, so like we said here, this limit is equal to this limit, so the middle limit must be the same. All right. Any questions before we move on? No. Okay. There's plenty of squeeze theorem type problems in the tutorial, but remember, it doesn't tell you to use the squeeze theorem. You need to know when to use it. Okay, so again, the three things we can use, we've got the limit laws, we've got the squeeze theorem. Later on, we will have a look at the L'Hopital's rule. So for now, when you're looking at the tutorial, you need to think of the limit laws and the squeeze theorem. Okay, the question won't tell you what to use. You need to figure out what you need to use. Okay. Again, any questions before we move on? No. Okay. Okay. Example 2. We have the limit as x, limit x goes to 0, sine of x over x. We want to show that this is equal to 1. Okay. So this is going to be a proof type question. So we've got this limit is equal to 1. We want to prove that the limit is 1. So prove that this limit has the value 1. Okay, this proof is quite long. Please make sure that you understand it. Okay, so the way that we prove it is not by using any algebra technique that we had before. We're going to prove it using a geometry proof. Okay, you're familiar with Euclidean proofs from grade 12? Yes, good. Okay, so we're going to construct a circle. Okay, roughly a circle. Okay, we've got some origin point and a radius. And then we've got a triangle like so. Okay, so we construct this. So we've got a unit circle. So you can write here radius 1, unit circle. We've got a radius going out and then another radius going out, but we extend it further to end up with this right angled triangle. Yeah. In other words, that vertical line is going to be tangent. Okay, so we've got a radius, we've got a tangent, and then we connect it up to make this right angle triangle. Okay, the next thing we do, that intersection point between the extended radius and the circle, we're going to make a perpendicular line going down, and this will be perpendicular as well. So the tangent line and then this new perpendicular line, they're both perpendicular to the radius. Okay, which means they are parallel. That will be important in a bit. Okay, that's also a radius, so we can mark that as 1. Okay, now we need to label the points. So the origin, that's usually O, and then let's call this A, B, C, and D. Okay, so that is the construction for this. So what we want to do now is use the squeeze theorem along with this picture to prove this limit over here. Okay. So again, how do we use the squeeze theorem? We've got something in the middle. That's what we want to prove. That's what we want to find. And we bound it between two other functions where we can take the limit. So that's what we want to do in this case. We're going to have this sine x over x. That's going to be in the middle. And then on the left and on the right, we're going to have some other functions where we know the limits already. Okay. So how do we do that? Okay, so let's write what we want. So the aim is to build an inequality where the middle term gives us the limit we want. So that's the aim. And if we can do this, we can then use the squeeze theorem on all three parts of the inequality and get the limit that we want. Okay, the way we're going to do that is by making an inequality of areas. So over here, in this little picture here, we are going to have three different areas where one is bigger than the next. So OAD, that's a triangle there. We're going to find out what that area is. And we see that's smaller than the slice OAC. If we look at like a pizza slice, okay, we're going to cut it out like a pizza slice. OAC, that's a larger area. And then finally, OBC, that's a larger triangle. That's going to have the largest area. Okay. So everyone see what we're doing? We're going to have a smaller triangle, OAD. That's going to have the smallest area. That is going to be less than or equal to the pizza slice OAC. Okay, just have a look there. OAC, that's the next biggest area, which is now less than or equal to the largest area, OBC. Okay, so we've just got a short sequence of areas there. Okay, so we want the area of triangle OAD. Okay, so OAD, that's the first one that I mentioned. That's the smallest one. Okay, this is going to be equal to half base times height, your normal triangle area. So it's going to be 1/2 the side length OD times the side length AD. Right, half base times height. Okay. Now, what we're going to do is do a little bit of trig now. Okay, so that angle in the middle there, we're going to call this angle X. Okay, so we can call that X, and we're going to use a little bit of trig to work out sine X, cos X, tan X from this. Now, it's quite easy because the base over there, OC, we said that radius was 1. So that fits 1. And then that other one there, OA, the other radius of the circle, that's also 1. So if we're looking at that triangle, that hypotenuse there is just 1. Okay, so the trig ratio is quite easy to do. So this is going to be 1/2 OD. That's the adjacent, so that's just cos. So cos X. And AD, that's the vertical, that's just sine X. Again, the hypotenuse is 1, so we don't need to worry about that. Okay, everyone still with me? Okay, so we put the angle X, and we use trig to find the ratios for the sides of the triangle. Yeah, that's all we're doing. Next, we look at the bigger triangle. So area of the triangle OBC. Okay, so triangle OBC, that was the largest one. Again, it's just half base times height. Okay, what's the base? The base is OC, and the height is BC. Okay, again, a little bit of trig. OC, that has length 1, because we said this was a unit circle. BC, that's just going to be tan X. Okay, so this is going to be 1/2 tan x. Okay, again, we're just using the trig ratios, right? Opposite over hypotenuse. Okay, anyone lost? No. Okay, good. Cos, sine, and tan, sure. So OD, that was this bit over here. That is the adjacent of that triangle. Okay, the hypotenuse is 1, so the adjacent will just be cos x. Right, because we got x, adjacent is cos x. Okay, then AD, let's put that in red. AD, that's the opposite over hypotenuse. The hypotenuse is just 1 again, so that will be sine x. Right, because sine x is opposite over hypotenuse, but the hypotenuse is just 1. And finally, the last side we needed was this BC. Okay, that's the opposite. The adjacent is just 1. Opposite over adjacent, that's tan. Yeah, so BC, that will be tan x. So in blue here, that will be cos x, because that's the adjacent. The red, that is sine x, that's the opposite. These are just your trig ratios. You've covered that before. And then lastly, BC, that is the opposites over adjacent, right? Because we know the adjacent is just 1, so that will be tan. So that's tan. Okay. Just normal right angle triangle trig ratios. Any other questions? Okay. So we got all of that. And then finally that pizza slice that I said, the OAC, if you imagine that as a pizza slice. Pizza slice isn't the correct word, but you can write that as area of the sector. It's pen. So you can think of it as pizza slice, but the correct word is sector. Get to that now. Yeah, there we go. So area of the pizza slice. Yeah, again, the correct word is sector of OAC. Okay, how are we going to find that? Perimeter. 2 pi r, thank you. Okay, so the total perimeter is 2 pi r. Okay. Please make sure you know that. If you don't know that, there's going to be problems. Okay, so the total perimeter is 2 pi r. So again, instead of looking at it as 360 degrees going all the way around, we look at it in terms of the perimeter. Okay, so 360 degrees going around, that's degrees. We're not going to do that anymore. 2 pi r going around, that's the full perimeter. That's how we work with radians. Now imagine this was a unit circle, then r would be 1. Yeah, so what we do is we imagine a unit circle. So that just has length 1. Going all the way around, that's going to be 2 pi. So 2 pi, that's going to be equivalent to 360 degrees. Then if we take some portion out of this, so some angle theta, that theta will be some fraction of 2 pi. Like a degrees is some fraction of 360. Like 90 degrees, that's 1/4 the way around. That gives you 90 degrees, 1/4 the way around. 2 pi, that's all the way around. Pi over 2, that will be pi over 2. How far around do we go? Okay. 2 pi, we go all the way around. Pi over 2, how far around do we go? quarter. Okay. Pi, how far around do we go? Half. Okay. Yeah. So just keep that in mind. So here, pi, we went halfway around, so that's 180. Okay, we're just looking at the relationship between the two. So if 2 pi is all the way around, that's 360. Pi, that's halfway around, that's 180. Pi over 2, that's 90. That's a quarter way around. And we can look at any fraction like this. So pi over 4, that's one of your special angles. That'll be 45. Okay, pi over 6. 30. Yeah. So all of your special angles from degrees, we can convert them to the new radians, right? By the fraction of 360. So 90, that was a quarter, so it'll give you pi over 2. 180, that's a half, so that's pi. Okay, you can go between the two. And then the last special angle, pi over 3. 60, yeah. Okay, so we can go between the two. And that's it for radians. Yeah, that's it. So in degrees, again, you go all the way around, that's 360. You go a quarter way around, that's 90. You're just measuring it in terms of some fraction of 360. Okay, halfway around, 180. We do exactly the same thing for radians, but instead of looking at 360 bits going around, we look at the perimeter of the unit circle, which is 2 pi. So all the way around is 2 pi. Halfway around is pi. Okay, 60, that will be pi over 3. And you can convert between the two. Okay, so that's how radians work. Later on, when we look at the trig functions, we'll look a bit more into this. But for trig functions to work with differentiation, we have to use radians. Yeah, that's the key points for using radians over degrees. When we do the derivative of trig functions, if we use degrees, it's ugly, it doesn't work nicely. If we use radians, it's very nice to work with. Okay. Okay, so we use radians over degrees. So that trig derivatives are easy to work with. Okay, so we'll only look at this next week when we do the derivatives. But for now, just keep in mind when you're working with any trig functions and so on, we need to be using radians. Okay, if you do use degrees next week and so on, instead of radians, all of your answers will be wrong. Okay, it's a issue. Okay, so if you're using degrees, the answer's wrong automatically. Please make sure that you start using radians. Okay, and start thinking in radians as well. So before, when you thought 360, you must now think 2 pi. Before you were thinking 90, you must now think pi over 2. So in this week and next week, you must start rethinking to radians. Okay, there are exercises in the textbook. I'll put them up for you to try, but just get in the mindset of radians from now on. Okay, so we've got x here. Now we're not using degrees, we're using radians. So we want to find the area of that pizza slice, OAC, given the angle x. So how can we do this? So let's look at the pizza slice again. So this was OAC. And we want to find the area of this. Again, given this angle inside here is x. Okay. So we're going to use radians to think about this. We know that all the way around is 2 pi. We're only going x around. So what is the proportion of the amount going around compared to the full pizza? It will be x over 2 pi. So we're only going around x. The full amount is 2 pi. Okay, in terms of the angle. So that little angle is x. The full angle is 2 pi. What's the ratio? It's just x over 2 pi. Now this must be equal to the ratio of the areas. Okay, the ratio of the angles must be the same as the ratio of the areas because it's the same amount that we're going around. So what area do we want? We want that OAC area. Okay. And what's the full area going to be? Okay, we got the circle. What's the full area? Yeah. Yeah, full circle. Full circle. What's the area? Pi r squared. What's the radius? 1. Yeah, we said it was 1. Right at the beginning, it was a unit circle. So the area is just 5. Yeah. Okay. Make sense? No. Okay. So what we're doing is we're looking at the ratios. Okay, so we got this angle x, meridian, x here. Remember, x, we're working in terms of the perimeter. That's how radians work. So x is this bit, or you can think of it as AC, that little section. So the ratio of AC, this length, over the full length, the full circumference, what is that? This angle is x. What's the full angle? So what's the ratio? X over 2 pi. Okay, good. So we got that part. Everyone's okay with that? Let's look at the other part. This ratio of the angle must be the same as the ratio of the areas. Do you see that? The same piece, right? X being the angle piece, or x being the pizza slice piece, it's the same piece. So the ratios must be the same. Okay, so what is this area going to be? OAC, that's what we want. Okay, so that's this top one. What's the full area of the pizza? Pi r squared. What's the radius? 1. At the beginning, very first thing we did was draw a unit circle. So pi r squared, if the radius is 1, we get pi. These must be equal. It's the same ratios. Okay, so we get that 1/2 x is equal to area OAC. Again, this is just the pizza slice. Okay, everyone okay with that now? Okay, good. So let's go right back to the beginning. Okay, over here. Okay, so what did we want? The aim was to build an inequality where the middle term is the limit that we wanted. That middle term, that's the sine x over x. Okay, that's what we want. So what we're going to do is build up that inequality using these areas that we've now found. We found the smallest area, we found the largest area, and this pizza slice bit, that is the middle area. Okay, and one is smaller than the other. So let's look at the smallest area. That was the OAD area. That was this, half cos x sine x. So that's the smallest area. Let's put that first. This is less than or equal to the pizza slice area. We have that above there, half x. And this is less than or equal to that bigger triangle that went outside the circle. That was the OBC area. That was the largest one. That was half tan x. Okay, so that was the largest area. Okay. So all I did was I took the 3 areas and I put them in order. We got the smallest triangle first, pizza slice, and then the larger triangle. Everyone okay with that? Uh, there's the power there. There's the power there. I cancel that. So you can put your cross out if you want to do that. Okay, so we've got the three areas in order. Now we can simplify a bit. So we got a half, half, and a half. They can go. Okay, they got. Okay, next, tan we can write as sine over cos. Okay, good. Now we've got sine x on either side. What we want is the sine x to be in the middle, because the middle is the goal, right? Again, don't forget what we want. We want sine x over x. Okay, so over here, we want sine x to be in the middle. Let's divide everything by sine x. Okay, so I'm just dividing through by sine x. Now, in the middle, we've got x over sine x. What we really want is sine x over x. So let's flip everything. So we're going to have 1 over cos x is greater than or equal to sine x over x greater than or equal to cos x. Okay, so I've just flipped everything. Okay, remember the inequality flips when you do 1 over that thing. Okay, so 2 is less than 3, but if you flip it, then a third is less than a half. Okay, and now we can do the limits. So we're going to have the limit x goes to 0 of cos x is less than or equal to the limit x goes to 0 sine x over x, which is what we wanted, and it's in the middle, which is good. And this is less than or equal to the limit x goes to 0 of 1 over cos x. Okay, so now we've set up everything for the squeeze theorem. Okay, so we took the inequality of the three areas and we've converted it to this inequality of limits. Now we can just take the limits. So the first one, limit x goes to 0 cos x. What's that going to be? 1. Okay. Limit x goes to 0, 1 over cos x. What's that going to be? 1. Okay. The left side is 1, the right side is 1, the middle must also be 1. Limit x goes to 0, sine x over x, the middle one, which is the one we wanted to show, must be also 1, because the left and the right was 1 as well. Okay, by the squeeze theorem. Okay, and that's it for the proof. Right. Any questions on this last part that we did? Yeah. The denominator, the start. So we've got 1 over cos x. What happens to cos x when x is 0? 1. So we get 1 over 1, 1. Yeah. Or you could have done it with the limit laws. Limit of the top is 1. We take the limit to the bottom, that's also 1. 1 over 1 is 1. Okay. But you don't really need the limit laws. We can see the bottom is going to be 1, so it's 1. Okay. Any other questions? Oh, good. Yeah. Sorry? You're still writing? Yeah, no, you can still write. I want to know if there's any questions. So everyone's okay with this last bit using the squeeze theorem? Yeah. Sorry? No, this isn't the squeeze theorem proof. This is just an example using this. Yeah. Always going to be 1. You mean the answer for this being 1? Yeah, this is 1, but for other cases, it depends on what's given. Yeah, we'll see a lot of the times it will be 1 or a half or something like that, but it always just depends on what's given. But this one here, you could just memorize as being 1. Because we've done the proof, you know it's 1, you can just stick with that. Okay, so we've proven it, we know it's 1. So in the tutorial, when this comes up again, you don't need to do the whole proof, we've already done it. We just know it's 1. Okay, you don't need to redo all of that work. Okay. Same goes for the test and stuff. If this comes up, we know it's 1. You don't need to redo everything. Okay, any other questions? Okay. Yeah, last year when I had the other class, everyone had questions on this. No, if you don't have questions, that's fine. Okay, everyone copy this down? Sorry? Yeah. Okay, please copy it down quick. Whatever we don't go through today, that's left for homework. Okay, so we've got until 3. If we don't finish, the rest is up to you to learn. Okay, so please copy down quick so we can move on. Yep. Yeah. No, that's just the radius because we're working with the units. Yeah, if you change that one, that will change. But we wanted to show that this is 1, so we use units. If this was like showing it's 2 or something, then yep. Stop. Yeah, sure. This bit. Oh, just to review the thing. Okay, sure. Okay, sure. Okay, so we've got the unit circle. Okay, so we set up a unit circle. What we want to do is set up 3 areas where we've got a smallest area, a middle area, and a largest area. Okay, so for the squeeze theorem, we need something less than equal to something less than equal to something else. So we set up the smallest triangle, OAD. That's the smallest triangle here. That's area number 1. Then area number 2, a little bit bigger, will be OAC, this pizza slice part. That's the second area. And then finally, the largest area is OBC. That's this bigger triangle being extended out. Okay. So what we want to do is find the areas of those triangles. So area of triangle OAD, that's going to be half base times height. Okay. So how do we do that? Well, what's the base? That is OD. That's the adjacent in this triangle. The adjacent is cos x, trig ratio. Okay, so base is cos x. What's the height? That's the opposite. Trig ratio for the opposite is sine. That'll be sine. So it will be half cos x sine x. And that's what we got over there. half cos x sine x. Okay. Next one, let's look at the biggest triangle, the OBC. It's half base times height again. What's the base? OC. That's the radius. It's a unit circle. That's 1. Okay. What's the height? Okay. We know the hypotenuse is 1. This is 1. So we're interested in the adjacent and the opposite, because we know what this is already. So the adjacent is this full length, which is 1. This OC is 1. We want the opposite. We've got the adjacent. We want the opposite. What trig ratio is that? Tan. So it's tan. So that gives us this here. Yeah?
When we're doing the limits with the trig ratios, are we always supposed to use the triangle? Sorry, it's circle.
Yeah, I mean, trig is always with circles and triangles. Yeah. Whenever you got trig, think circles, triangles, like you did in high school. Okay, that's the only way to introduce trig ratios. You draw a right angle triangle, angle x, you know the other sides. Okay, so we got that. Then we needed the pizza slice bit. Okay, so over here. So that shaded pink region there, that is the same as this full region here, the OAC bit. Okay, so how do we get that? Okay, so we got x. Okay, again, like I said, if you use degrees, you end up with the answer being pi over 180. That's not nice. We don't want that. But here we've got angle x. We use radians. Okay, so x, that's this angle. So let's put a little angle bit there. So green, that's this angle we're looking at. No, blue, that's the full one there. Yeah. So the green bit is x. The green bit plus the rest of the blue bit is all of it. And that's 2 pi. So the green bit is x. The full bit is 2 pi. What's the ratio? X over 2 pi. Okay, good, we got that. Now, what we want is the area. Right? Because we have smaller area, medium area, large area. So this area is OAC. We've got that at the top. If I have 1 pizza slice out of 8 pizza slices, what's the ratio? 1 over 8. You eat 1 pizza slice, you've got 8 pizza slices, that's 1 over 8. Okay, the area of the pizza slice is what we want. The other slices make up the full area. What's the full area of this? Pi r squared. That's the radius. 1. So this is 1 pizza slice. This is all of the pizza slices, pi r squared. The radius is 1, so it's pi. We've got pi here, it cancels. And we just get half x. If we use degrees, this would be x over 360. And then this would be divided by 360. With the half here, will be x over 180. And it's going to make a mess. Yeah. But if you use radians, this is pi, that's pi, it cancels nicely. If you use degrees, you end up with 180s all over the place. It's just a mess. But we'll see that later on. Okay, maybe you can try that for homework. Homework. Okay, repeat this using degrees and show that the limits x goes to 0, sine x over x is equal to pi over 180. Okay, that's a horrible number. We don't want pi over 180. It's much better having it being 1. If you use radians, the answer is 1. If you use degrees, the answer is pi over 180, but we don't want that. Okay, homework, try that out with degrees. Okay, any last things to say before we move on? All good. Anyone still copying it down? Okay. I did warn you, whatever we don't cover, that's for reading at home. Okay, we're on a very, very tight schedule for the year with the amount of work we need to cover. If we don't finish it in class, you need to finish it yourself. It cannot carry over to the next week. Okay, there's really not enough time. Yeah, tell me when you're ready, then we'll carry on. Okay, just a note with the workload. If you think this is a lot now, you will not survive engineering next year and the year after. Okay, so just keep in mind this workload now that we've covered in the last 4 weeks. If you cannot keep up with that, when you get to Math 238, not next year, the year after, you're going to be crying. Okay. No, like actually, my second years from last year, they're telling me, so we can't keep up, can't hear the lecturer, don't know how to do the work. So help me. I'll say, I'm not your lecturer, I can't help you. And that's the top students telling me, they're telling me it's a lot. Okay, so please, when I say engineering is a lot, it's a lot. Especially when you get your chemical engineering, you got your chemistry modules and your math modules and your other math modules, it does pile up. Okay. Everyone copy this down? Can we continue? Yes, okay, good. Okay, continuity. Okay, so definition. A function f. Okay, and again, just to reiterate, I'm just saying it's a function. It could be a parabola, it could be a hyperbola, it could be a piecewise function. Some function f. So function f is continuous. Okay, so we say it's continuous at x equals a if the limit as x goes to a of f of x is equal to f at a. Okay, that is the definition for continuity. The limit agrees with the function value. Now remember, when we write down this limit, we mean two things. So this limit as x goes to a, what we really mean is limit x goes to a minus and x goes to a plus. So this actually means the limit x goes to a minus is equal to the limit as x goes to a plus. Okay, we covered that on the Thursday. So a limit exists if the left limit and the right limit agree. Okay, so please make sure you make notes of that in this definition here. So the left limit must equal the right limit, must equal the function value. There's three things you need to check. Left limit, right limit, function value. If all three agree, then it's continuous. If one of them doesn't agree, it is not continuous. So otherwise, it is not continuous. Okay, or we can say discontinuous. Okay, and one of those three need to break, and then it's discontinuous. Okay, and then just a little note. A function f is continuous on an interval. Okay, remember intervals from sets. So on an interval, if it is continuous at all points on the interval. So we know how to do continuity at a single point. If you want to check if a function is continuous on an interval of points, you need to check all the points for it to be continuous. Okay, let's have a look at some examples. Okay, so we've got some function looks like this. Okay, so we've got this function here, and we've got the points A, B, and C. Okay, the dot over there at C is just part of the curve. I just made it bigger for emphasis. Okay, so some points on the curve. Okay, let's have a look at all 3 points and check, is it continuous or what breaks the continuity? So at A, okay, limit from the left is there. Limit from the right is there. Where's the function value? Here, because it's a closed dot. So again, limit from the left is here. Limit from the right is here. The function value is also here. So the limit from the right agrees with the function value. It does not agree with the limit from the left. It is not continuous. We say there is a discontinuity at A. Let's look at B. Limit from the left is there. Limit from the right is here. Limit from the left equals limit from the right. So the limit exists and it's this value here. What's the function value here? Undefined. There's no function value here. The limit exists. The limit has a value. The function does not have a value. It is discontinuous over here. And C. Limit from the left is here. Limit from the right, we follow the curve, is here. The function value is also here. The function is continuous at this point. Okay, so please make notes of those 3 cases. Okay. Another way of describing A and B discontinuities. A is a jump discontinuity because the left and the right limit do not agree. It jumps from bottom to top. It is called a jump discontinuity. B is called a removable discontinuity. Why? Well, we can just fill in the dots. And now the discontinuity is removed. Okay, quite literally. We will see in an example, you fill in the dots, the discontinuity is removed. So we call that a removable discontinuity. And C, it's continuous. We don't have to say anything more about that. Yeah. Yeah. So this one is a jump. This is removable. Okay. Jump is just jumping. Jump discontinuity. It's just a name. It's just the name we give it. Yeah, so you go along here, you jump up to here, you've passed a jump discontinuity. Just a name for it. I mean, you can just, or B and C are both discontinuities, but if you want to separate them into 2 parts, the first one is called jump, the second one is removable. It's like a subcategory. Okay, just some notes on this. Okay, so all of this in the notes is without proof. So we can just take it as a given. You don't need to prove any of this. So polynomials are continuous everywhere. Okay. So if you are given a polynomial, you immediately know it's continuous everywhere. You do not need to do any checking. We take that as a given. Okay, rational functions, we know what these are continuous everywhere on their domains. Okay, and we know how to find the domain of a rational function. Okay, trig functions are continuous everywhere. On their domains. Okay, and then just a note, this is in radians. Okay, so again, when you see trig functions, please start doing that conversion from degrees to radians. So the sine function, you would think 0 to 360. Again, please now think 0 to 2 pi. Okay, so this week, next week, please start making that transition from degrees to radians. Okay, so after next week, it will be exclusively radians. Please do not get left behind. Okay, when we start talking about radians with the domains. Okay, exponentials are continuous everywhere. Okay, so it's like your 2 to the x, 3 to the x, exponentials, logarithms are continuous everywhere. On their domains. But, you know, logarithms have that problem with negative values and 0. Okay, so when we say logarithms and their domains, that's from 0 onwards. Okay, 0 and negative logarithms have a problem there. Okay, so these are just a few functions, or a few function types that are continuous. We will be adding to this list, but for now, we can take it as these functions are continuous, so they satisfy the continuity property. You can use it without proof. Lastly, power functions. Okay, like root x, cube root x, all of those power functions are continuous everywhere on their domains. Yeah, and we will add to this once we look at some more functions. Okay, so next week when we look at the hyperbolic trigonometric functions, we're going to be adding it to the list as well. Okay, theorem. This is also without proof. We can just take it as is. If f is continuous, we know what that means. If f is continuous at b, some point in the domain, it's continuous at b, and the limits as x goes to a of g of x is equal to b, the same b where f is continuous, then, and this is very, very important, the limit as x goes to a of f of g of x, so we're taking the composition of f and g, is equal to f with the limits inside. Limits as x goes to a, g of x. Okay, and this will be f at b. This is very, very, very important. Please put a big exclamation mark next to that. Okay, so what this theorem tells us, again, without proof, you don't need to worry about that, is that for continuous functions f, the limits and the function can be swapped. So here we're taking the limits of the function. Over here we're taking the function of the limits. We have swapped the two. This only works for continuous functions. Okay, and it's very important when we look at some more limit examples tomorrow. So for example, So this we'll only look at tomorrow, but just to give you an idea, limit x goes to infinity, square root x squared plus 1 over x squared minus 1, for example. We want to find out what this limit is. Now, this root here is a power function. We know that is something to the half. It's a power function. It's continuous, which means the limit can go inside. So this now becomes the root of the limit x goes to infinity, x squared plus 1 over x squared minus 1. So just given like this, it might be difficult. How do you do the limit with the root? But the root is continuous, so the limit can jump inside, and we can end up with this. This inside part we can do, and then we just take the root of the result. Okay. We will see this many, many times as we do more complicated limits. Okay, so again, just a little note. If f is continuous, then the function and the limit can be swapped. Okay. So if you have a continuous function and a limit, if the limit's on the outside, you can take the limit inside. If the limit's on the inside, you can take the limit outside. It can be swapped between each other. Okay. Any questions on this theorem? No questions. Everyone's okay with what it means. Okay. And then the last thing for today, classification of functions. Oh. Okay, so we'll do the first 2 bits of this, and then the remainder will come as we do derivatives. Okay, so firstly, the set of all continuous functions on a domain D is given by C0D. Okay, so this is a set, just like we had sets before, but it's not sets of numbers or sets of letters or anything like that. This is a set of functions. So this is the set of all functions f, such that f is continuous on D. Okay, where D is some domain. Usually D will be the set of all real numbers. Like polynomials, the domain is the set of all real numbers, exponentials, certain trig functions, and so on. But for here, we'll just put D. Okay, and then we'll just add this little bit. We'll add more as we go on. So the sets of all continuously differentiable functions on a domain D is given by C1 of D. Okay, so what do we mean by continuously differentiable? It means if you give me some function, if I do the derivative of the function, and we know what that means. If we do the derivative of the function, we get some result. That result is, again, continuous. Okay, so given a function f, if it remains continuous after doing the derivative, then it belongs to C1. If it remains continuous after 2 derivatives, then it belongs to C2. If it remains continuous after k derivatives, it belongs to CK. So this continues down. So CK, that is the set of all k times continuously differentiable functions. Okay. For example, if we have x cubed, okay, that's an example of a k times continuously differentiable function, because you can take the derivative once, that will be 3x squared. Okay, from high school, you know that. Okay, take the derivative again, that will be 6x. Take the derivative, it's continuous. Take the derivative again, it's 6, that's continuous. And you can continue like that. Okay, so that is k times differentiable. Okay, and then the last one before we go today, that is C infinity D. Okay, this will become very, very important later on. This is the set of smooth functions. What that means is we can do the derivative as many times as we want, and the result is again continuous. Yeah. So some examples and non-examples we will look at next week. But the idea of C infinity or smooth functions is that you can do the derivative once, twice, 3 times, 4 times, 5 times, as many times as you want, and the result is again continuous. Okay, does make sense? No. Why not? Where did I lose you with that? Okay, you know what continuous means? Yes. Okay. If I give you a function f and you differentiate it once, can you check if it's continuous? You know the definition. You can check if it's continuous. If you do it twice, can you check if it's continuous? Yeah? Like the example with x cubed. X cubed is continuous. You do the derivative. You get 3x squared. That's continuous. You do it again. You get 6x. Is that continuous? We do it again. That's 6. Is that continuous? Yes. We do it again. We get 0. Is 0 function continuous? Why not? Why did you say no? Look at the definition. Don't guess things. Look at the definition. So the definition for continuity is left limit equals right limit equals function value. So let's look at the 0 function. That's just always 0. So it looks something like that. It's always 0. Let's pick a point. Let's pick this one. What's the limit from the left? What's the limit from the right? What's the function value? Is it continuous? Pick another point. What's the limit from the left? Limit from the right? What's the function value? The continuous? Pick another point. Limit from the left? Limit from the right? Function value? Is it continuous? Now pick another point. Is it continuous? Is it continuous everywhere? It's continuous. Yeah. Whenever you're in doubt, check the definition. Always. Never guess things. Always check what the definition says. Okay. So with that, you can differentiate it as many times as you want. It's still continuous. So we call it smooth. Yeah. So for this year, we're going to be dealing with these smooth functions, okay, from now on. So piecewise functions, all of that other stuff, we're going to look at a little bit in derivatives. But after that, we are only going to be looking at smooth functions. Okay. Which means in tests and exams and so on, you can assume the function is smooth. And you can use the properties of a smooth function. After that, we get one more, which are the analytic functions. Those are smooth functions plus a little bit. We're going to look at that next year. Okay. So smooth functions this year, you can assume the functions are smooth. Next year, we're going to look at analytic functions. Now, next year, when I ask, do you remember smooth functions and analytic functions? I hope everyone says yes. Okay, so please make a note and keep your books for next year. Smooth functions and analytic functions. Just add the little note there. Okay, so again, C0, continuous. C1, continuously differentiable. CK, you can do it k times. C infinity, you can do it as many times as you want, also known as smooth. One more condition we're not going to look at now makes it analytic, and that will be important for next year. Okay, so please make a note of that. Okay, any questions on this? Okay. Yes. The limit can be swapped. Yeah, so that is the definition of continuity over here. So let's have a look at that. Okay, so this is just the theorem. Okay, we take it as this. So here we are taking the limits of the function. This comes second. Okay, so limit first, function second. What the theorem tells us is we can do the function and then the limits. Now the limit comes second. So we swap that. So here, this is limits of the function. This is function of the limits. They've been swapped. Yeah. We'll see this in this example here. Like this. Limits of a function. We can put the limit inside the function, so it goes inside here. Okay, that's how we use it. Okay. Any other questions on this? Oh, good. Okay. So last bit here. Okay. So we got C0, C1, CK, C infinity. These are all subsets of each other. So we won't be using this much this year. Next year, this will be important. Okay. So we've got C infinity as a subset, subset CK, subset C1, subset C0. Okay, this we will be using next year. Okay, this bit here. Okay, any questions on what we covered today? Okay, so 4 important things. Limit laws, please memorize them. They won't be given to you. Squeeze theorem, please make sure you know how to use it. The proof of sine x over x equals 1, please learn that. That was number 3. And then number 4, please make sure you know this, this box. Okay, those 4 things, please make sure you remember them from today. Okay, anything before we leave? Oh, good. Okay.